Hi everybody, welcome to session 7 for Intro to R. A few notes from last class. The t-test has two ways of input. One is a formula and the other is a couple of vectors as input. You want to be careful when using the t-test and know which one is which. So in this example we want to load the empty cars data set. On the left hand side you can see the head of empty cars, and when you do a t-test using vectors, make sure that you're separating the two groups or two categories of a particular variable. So in this case we have MPG for those observations that match the V-shape 0 category, and the second vector is MPG for the observations that match the V-shape is 1. So the input for that t-test would be two vectors, and one vector will be for all the categories of 1 of the second variable, and the second vector will be corresponding to all the categories of that second variable. So here's an example of how to use width, and what width does, it avoids you using any extraction techniques here. So empty cars $VS will give you the vector, but when you're using width, you'll get you don't have to use the $ to extract VS, because it will know where VS is coming from, the input for the width. So the first input for the width function is the data set, and VS will correspond to that data set. So you may feel like entering something like this to the t-test function, which is your MPG vector and your VS vector, and running a t-test on that, but it will run a t-test for those two variables as if those were the two groups. And what we want to do is we want to distinguish the two groups within the MPG variable. So we would do it as we saw previously up here. We would just take all the observations for one category and separate the two. So it might be easier to use the formula notation for the t-test. So if you do MPG tilde VS, that will give you the right result. So you'll see that the mean in group 0 and the mean in group 1 are close. So if you do it the wrong way, you'll see that the means are not even close, because in the Y input, VS is 0 and 1, so you'll get a mean closer to 0.5 or 0.4 here in this case. So you have to be careful when entering the inputs of the t-test function. So if we do it the first way on line 5, we'll see that the means are pretty similar because we've divided our vector into two pieces. So we can also look at those MPG values for where VS equals 1. So I can do width empty cars, comma, MPG VS equals 1, and you'll see those are what the actual inputs to that t-test call at the top here on line 5. So we're comparing these two vectors to each other and seeing whether the mean of the two vectors is significantly different from each other. So that's the type of input that we want to give the t-test if we're using vectors. So you may see some objects with periods in R, and when you're creating an object like this, it just means that it has a period in the name. Sometimes you may see functions with a dot in the name, and that indicates usually that it's a method for a particular class. So as we've seen previously, we see as dot data frame. That is a method for the data frame class. So you may see dots in objects, but they don't mean as much as dots in functions. So when we see functions with dots, they may have more meaning than just a dot within an object name. So that's something to look out for, and nothing to worry about if it's an object name with a dot. And here we're assigning the output of the lm function and calling it orange.lm. So remember that we can apply a function over the columns of a data frame, and we use lapply for, as we've seen in previous examples, we use lapply to test whether all the columns in the data frame are numeric, and we can run that, and you'll see that the output is a list. But when we use vapply, we have to specifically give a function value that's returned. So in this case, because isNumeric returns logical, we'll tell it to expect logical. So when we run that, that'll give us a vector output instead of a list output. That's what vapply does. And we can assign this fun value in several different ways. So we can use true, or we can use false. As long as it's a logical value, it will understand that it should look for that type of output from the function here. So for creating factors, remember we can add labels, and for the VS class, or the VS variable here, we add a couple of labels, V-shaped and straight, to give our variables a bit more of information. And remember that if you want to drop columns from a data set, you can use the negative sign and then the column name. So this is using the tidyverse. So remember that whenever we're using a package, the function in a package, we want to use library first and then the function name. So in this case, select accepts empty cars as the first argument, and anything after that will indicate that you're dropping or selecting columns from that data frame. There are other ways to remove columns, as I've shown you in class, and one way is to match against the names of the data frame. So we can break this down into several pieces. Here we have the names empty cars, which gives me all of the column names in the data frame, and I want to match that vector with instances of VS. So VS is one column that should be in empty cars. So when I run that, I get a logical value that will say in what position VS is by giving you a true value. So now that I want to because I want to exclude this vs variable, you reverse the logic here, and we want to have a true value for all the columns that we want to keep. So we can use this as our input to the subsetting function. So remember, when we use brackets, we're subsetting a function, we're subsetting a data frame based on the rows or the columns. So here we have a bracket. So this is base R, remember? Base R uses brackets. And we are taking this vector and using it to obtain the columns that we are interested in. So we can do empty cars and the vector. Just fix the syntax a little bit here. So that will give me all of the columns except VS. Right, line 36 will give me, will subset or take all of the columns except VS. You can also convert logical vectors to numeric using this which function. So you can do which on that logical vector, and it will tell you what positions in that vector are true. So it returns 8 because the 8th position in the logical vector is true. And we can verify this by looking at line 34, running that, and we can count 4, 5, 6, 7, 8. The 8th one is true. So you'll get a result of true. And when we add a negative in front of this column position or index, we're removing that column from the data frame. So this operation here is the same as saying -8 in the column positions. So that will remove VS from our data set, and you can include multiple values. So you can have -7, -8, -9, and that will remove the columns from your data frame. So the subsetting operations are pretty versatile in what they can accept as input. So you can always give it a logical or a numeric or a character vector. So whenever we're looking for help with a particular package that we've installed, or we want to look at a list of all of the functions that are available in a particular package, we can use this function called help with an argument package and give it the name of the package. So if we don't have it installed, it will say that the package here is not found. So what we have to do is make sure that the package is installed first. So we do, in this case, on this computer, I don't have the package installed, but I can download it and install it fairly quickly. And then when I run that, now that I've installed it, it should give me the documentation here for everything available, all the functions and data sets available in that package. So you can see that this is a data package. So you'll have a number of data sets available for exploration. So more on this LM type of object. Remember that the class of orange.lm is LM itself, and that's because we run the LM function, which is a linear model, and it returns an LM type of object. and we can use summary on this to look at the model results. And then we can look at the summary documentation for LM objects. So remember how I said that some functions can have a dot, and here this is a function, summary.lm, which is a method for the LM type of class, right? So we have an LM type of object in our environment, and we're looking for more information about the summary method for these LM type of objects. So you'll get the documentation for linear model fits, and you'll see what options are available whenever you're using summary on that object. So you can have you have a correlation argument, symbolic correlation, and further arguments. So remember that troubleshooting is important. So being able to recognize an error and tracing your steps to where that error occurred is very important when using SAS and R. And you want to be familiar with your errors so that you have a strategy for working with errors. So if you try to load a package and it's not available on your system, you'll know that it will say package not found, or so if I do library for a particular package, you'll see that there's no package called whatever the package was entered. So you'll know that you have to install it first before you can load all of the functions available in that package. So as I said in the previous class, most of the errors that you get are because you were expecting something to be somewhere and R couldn't find it in that location. So if you were trying to load a package that's not there, R will give you an error that there's no package called XYZ. So another way to keep track of what's going on within the R session, you want to be aware of your inputs and your outputs. So it's valuable to look at the documentation and see where the return values of particular functions are located. So if I do question mark data frame, in the values section, you'll get what type of object is returned. So then you can run something after you get that result or that return value. So you want to know what's coming in and what's coming out and how to work with those. So if you're using the tidyverse, there are a number of functions that operate on tibbles or data frames, and usually those functions are good at just giving you back the data frame. So they have this endomorphic type of operations which accept the data frame and return a data frame, but they run an operation, so they're pure functions because you expect a data frame as an input and you get a data frame as an output. So ideally a function would be a pure function, but in the real world all of these functions can return different types of results. So you just have to be aware of what's coming in and what's coming out. And practice is key, because I can talk about R all day, but if you don't do it yourself, then there's no learning happening. So you want to get into the habit of typing all of these examples out and going through websites and following examples and learning from the console and any code that you run in your RStudio session. So make use of the online resources and the help pages. I posted a number of resources on Blackboard and in slides. So in this slide deck, I have a number of additional resources that I'll be going through in a bit. But the main idea here is to be curious about the software here. So if you have questions, like create examples that will answer your question. So if you're wondering what happens if you try to multiply a character with a number, you can just test it in the console. So you can say a times 3, and you'll say, oh, it gives me an error because it only accepts numeric values. So some things like that, you want to just run it in the console and see what happens, and then learn from that and keep pushing forward. So getting help within R, I mean, you want to look at the documentation. The documentation is pretty thorough and sometimes too technical, so it's understandable that you're turned off by this dense documentation, and you always have resources outside of R that will explain it or give you examples with more a general perspective. So getting help outside of R is also valuable, and we have a number of resources like Stack Overflow, which I've shown you in the previous class, where people ask questions and they get an answer for any problems that they're having. So if you go through and see what kind of issues people are having, you'll get familiar not only with what errors are usually cropping up, but how to solve them or how to work with those type of errors. So remember that when you have a script or R&D file, you want to run the code line by line until you get to the error, so that you can investigate further and see what's causing the error. If it's telling you that it was expecting some kind of logical value, you know that your input might be a bit different, so you have to adjust your input so that it matches the function. So we looked at how to explore objects in R, and this is very useful because you learn from these objects by running these functions on them. So in this case, we have a example here where we are loading the Haven package, and this Haven package will allow you to install or load SAS data sets. And if this link works, it does. So I can load a SAS data set from my files, the datasets folder, and I use this read_SAS function to load the data. Then so now that I have this data in my console, I want to just explore it and see what's in it, and take the first 6 observations of the data and see what it looks like, what kind of variables it has, and what type of variables or the data type that these variables are. You can also do head and tail, also dim to look at the number of rows and columns for a particular data set. and use all the other operations that work on these type of classes. So you're mainly going to be working with data frames, so just use dim names, row names, call names, and names, which gives you the variables in the data. Right, so sometimes you'll have data that isn't of the right type, so you may need to convert the type. So there are functions for doing that, such as type convert, and this will if your data is actually numeric, as you see here in some of these variables, they're read in as character, but you need to convert them to numeric. So you can do type convert to convert these automatically. So R will try to guess what type the data is and then convert it for you. So if I do class varchar here, we'll see that it's character, but if I just look at the first 6 observations of that variable, this is actually a numeric variable. So you can do type convert to get this into a number. So we can call it burrow num, and then you can do head. So you'll see that burrow num down here is an integer now that it's been converted to integer or a numeric value from a character which was supposed to be numeric. So there are other reader has a package the package reader or readr has a function similar to what type convert does, but notice how type convert up here from utils works on a single vector, and type convert here in the readr package with an underscore takes a data frame as input. So you want to just be aware of that, and you'll see that you can run it on your entire data frame and get a new data set that has conversions of type where appropriate. So now you'll see that varchar should be numeric here. So you'll see that it has a type double. So that makes it easier for when it's time to clean your data, or when you initially import it and you don't get the types that you want, so you can run this type convert function on it. So another function that may be useful when working with data is working with strings. And strings have a long history of being annoying or hard to work with in computing environments. So there have been a whole number of functions and software to just work with strings and text. So one of these is the grep function, and this is more of a Unix type of paradigm, I'd say, where the function allows you to search through a string with a particular pattern. So in case you're looking for all the variables that have a burrow word in them, you can use this function to get what any of those matches. So if we look at the grep documentation, you'll see that you have a lot of functions available, but in this case we're just going to look at grep, and you want to give it a pattern. Usually it's a string, and for once you start cleaning data and working with lots of variables, it may be useful to sort of learn what regular expressions are about, and how to use them to your advantage when it comes to selecting variables and renaming things without having to do it one by one. So in this example, I can search through all of the names in my data set for a pattern burrow and give it a couple of more arguments here, such as ignore case and value equals true, and that will return all of the variables in my data set that match that pattern. So this is extremely powerful when you have a ton of variables that you need to clean, and I have had instances where I'm cleaning data and I have a number of variables that are somewhat the same, and this data was collected over a number of time periods. So all of the variables are the same, but they have an ending that identifies it with a particular time period. So in order to clean that data set, I have to match all of those variables across the years and then remove the part where it identifies it as a particular time point, so that I can have consistent names throughout all of my data, and then I am able to merge all of the data together. So using grep is really useful because it saves you all the time from cleaning variables one by one and renaming things and finding a particular variable in your data set when you have a huge data set. So I would recommend it, and there are a number of tutorials and online resources for using grep. So here I have another example where it will just return the index. So instead of the name of the variable, you have the index. So when you say value equals false at the top here, you'll get the index for those variables that match that pattern. So another easy way to rename variables using this this pattern searching and replacing. So is this gsub function, and what it does, it will substitute any pattern that it finds with another word. So say I wanted to recode my burrow variables with this. I wanted to rename these burrow variables with burrow instead of B-O-R-O. I want to use burrow, the full word. I can do that by using gsub, and in this case it'll just give me the vector because I'm not replacing anything right now or setting it, so it will just give me the result. So you can see that for these variables, burrow, I have burrow instead of B-O-R-O, so I have burrow char and burrow num, but I have an issue here where it says burrow huh. So you have to be careful, and if you're more adept or familiar with regular expressions, you can use pattern searches, and this is where grep shines. You can sort of select only those strings that match a particular pattern. So in this case, this means that the name of that string starts with a burrow and has an underscore at the end. So if you do that, it will give you what positions match there, the burrow vars. So there are two variables that match that pattern, and you can use value equals true to have a look at what those are. And then if you use gsub here, so I'm just going to run this and show you what it looks like. I didn't set this, so I'm getting an error. But here I do gsub on those burrow values, so I get burrow num and burrow char. So those are the ones that make sense to replace instead of the other burrow. So here I'm substituting burrow with burrow, but only for those that match a particular pattern, which is the result of this expression up here. And then I'm renaming my variables using this names function and the index here, burrow vars. So this was the index that told me your variables are in this location. So 5 and 15, and I can use this type of operation to replace the names in my data with the new names. So when I run that, you'll see that I have burrow char now in the data and burrow num. So this is a small example of what you can do with a number of variables, not just a couple, when you have, as I said, time series data, and you need to homogenize all of the names across the different time points. So this is why R is very useful at doing things like that. So here I wanted to show you again how some values in a variable are really missing, and if you were to use a regression or some kind of model where you had to use burrow, maybe you wanted to keep 99 as missing instead of its own category, so you can set this to NA in this fashion. So first we select, so we can break this down into several steps. So the first step is to find what values in burrow are 99, and we do that using this logical vector. So we're extracting burrow from the data set, class DS, and we're looking for any 99 values in that data set. And this only works because burrow here is numeric, right? So that will match any numeric 99s. So if we're not sure what type a particular vector is, we can just do class on that vector, and you'll see that it's numeric down here at the bottom. So when in doubt, you can just run a class function or any of these exploratory functions to see if your input is correct. So here we have a logical vector, and we're going to use that to select all of those observations where burrow is 99. And then here we're saying, just give me the values of that burrow column that are 99. So if I were to run this left-hand side, you would see that this is just a table with 99s all down the column. So if I do an assignment with NA, that will replace all of those values with NA instead of all of those 99 values with NA. So then I can see that now those are converted to NA instead of 99, and I can run my analysis all the way through. So you can also see that you have a condition here where burrow is not equal to 99, so you can see that they're all true except those NA values, which you can't comment on. So when something's NA, R doesn't know, it can't compare it to an actual value, so it just gives you NA back. So remember, when we want to take a subset of the data, we can use this operation here where we only isolate the rows for our subset. So we're taking a slice, and we're only interested in the borough, the Bronx, which is number 1 here in the data. And so we're using the bracket notation, the data set, and a logical vector here. So that will give us all the values of all the observations for the Bronx. And notice that it will include any NA values in here. So if we do table Bronx 1 borough, maybe I didn't assign this. So if we do table Bronx 1 borough, use NA always, you'll see that it also includes any NA values because R is not able to compare 1 to NA. So if you want to exclude those NA values as well, you can do you can modify your condition statement here at the top, where borough is equal to 1 and it's not, and borough is not NA. So you can combine those two to just get all the observations or complete cases for a particular subset of the data. So you'll see that if you run a dim on those two objects, you'll have the difference is just those NA values that are no longer present in borough in the Bronx 2 object. So now we know how to subset by the columns. So if we use the bracket notation and a index variable or index vector here, we can just take 2 columns from a data set that way. You can also use a character vector here with the names of the variables of interest, or we can use the dplyr way of doing things, which is select. So you can enter the data set first, and then the variables that you want to keep in the rest of the function here. So you want to have a catalog of functions that are useful for a particular task, and what that is just being able to have a mental catalog of functions that will work when subsetting a data set, for example. So you know that you have select and the bracket method. So you don't have to know exactly how to use those functions, but if you just pull up the documentation, you can see how to work with those functions. It's impossible to know how every function works in R because it's really R is really big now and it has a ton of functions in it. So what I always do is I find a function and then look up the documentation to see how to use it if I forget, and look through examples and sort of use those examples to adapt them to my data set or data problem. So as I said previously, you have reference websites such as the R Cookbook by Winston Chang, and this is for ggplot2. And I also have I should have knit into a better Sorry about that, but this should have updated for some reason it didn't. Yeah, even the date is wrong here. So my PDF here is not building for some reason, but I will post the PDF with the new points on Blackboard, so you can follow along with that PDF instead. So I wanted to point out that there are a number of resources, including QuickR, which is a pretty good website, and it has a ton of examples to use. Also, R for Data Science is a textbook by Hadley Wickham, and it's thorough, and it has a chapter for all of the possible topics that you will encounter when working with data. Also, you have this handbook for statistical analyses using R, so that will give you some examples of how to run t-tests, how to run a linear model, and other statistical methods like clustering and so on. So now I want to go touch a bit on reshaping, and this is also part of your data analysis workflow. So once you've read in your data, you can work with it, and you read it in, you make sure that all your data is valid, you run some checks on it, you do some exploratory and data analysis to plot plot the actual data and see what's inside of your data set. And then you want to, if your data is in a shape that is not conducive to the analysis, you might want to reshape it. So there are a number of functions for doing that. The tidyverse provides the gather function, but there are other packages such as reshape2 that will allow you to reshape your data. So in this case, we are reading the Pew data set and loading the tidyr package. And remember, we can use this gather function to take all of the columns as the income and exclude religion here, and say that our value is n. So all the values on the inside are counts, so we can call it n, and then we'll look at a head of that data set. So now you'll see how the data has changed, and we have an income variable with all the categories that were previously across the columns. Now we have income categories down the rows in one column, and the counts for each religion in another column. So it's good to look through the documentation here and see how you can use the spread and gather functions. Spread will do the opposite. So gather will take a number of columns and put them into one column or a couple, and spread will do the opposite and spread your data out to a wide format. So the reshape, there's also stats reshape, which is a function that will reshape your data, as well as reshape2, which includes some functions for reshaping data. So there are a number of tools available for reshaping your data. You just have to be able to follow some examples and specify the arguments of that function. So here we have a data set called IndoMath, I'm not sure, I don't remember exactly what it's showing here. So it's the pharmacokinetics of endomedicine, or methicin. So you'll have, so this is time series data, and you have a long type of format here where you have repeated measurements across in time intervals or time points and the concentrations. So you can reshape that into a wide format using the reshape function and tell it the value names or value columns, the ID variable, time variable, and what direction you want to reshape to. So you can run that, and you'll see that now you have the concentrations in the columns, and you have one row per subject or participant. So you see how that how the data set is now represented differently. So that will allow you to see that, so this table function will allow you to see that there's only one subject per row in this data set. So we also have summarize and aggregate functions. So this also getting closer to your analysis phase of a particular workflow. So we've looked at how to combine or group our data based on a categorical variable using the aggregate function and the group by function. And you can see again how we can select or remove a couple of variables from our data, and you can either use the index. So this gives us an index here, so -8 and -9. You can also say give me all the observations which are not in these two, in this vector. So let me undo that and show you this as another row here. So remember that this in operator checks the values in a table. So it will look for any appearances of AM and VS in the empty cars variables. So if I run this part, you'll see that it says that for all the names in empty cars is the first one either AM or VS? No. And then it goes false, false, false until it finds AM and VS in the names of the empty cars data set or the variables. So you'll see how that works, and then you can do the inverse to just exclude those variables and create your subset. Now that we have a subset with just numeric variables, we can group by a particular variable such as cylinder and take all the data and aggregate it and get some summary statistics such as mean for each of those levels in cylinder. You can also do it for one variable using the formula notation. So to use all variables, use a dot, but for one variable, we just give it a particular variable, such as mpg or horsepower, and we're using the same function, mean. And then if you're using the tidyverse, you can combine these operations such as group by, then summarize, and have a table of results here, so you can get a mean for each of the categories in cylinder, but also standard deviation and n. So the counts. And then here again we have another, so we're removing more variables from this empty car data set and creating another, or the same, we're using the same name for that object, and then we run it through the pairs panel to do some exploratory data analysis. So you can see what variables are highly correlated against each other, and sort of figure out where your outliers are and what variables are almost the same or very different. And we have histograms and box plots using formula notation. You can also use this with function to run a plot on two variables or two vectors, and remember that you can always customize these plots to your liking, so you have a lot of flexibility at your disposal here. And then you can add A/B lines, regression lines, and that makes part of what the exploratory data analysis phase is. And finally, you'll run a linear model to predict or explain a particular variable in your data. So that is the typical analysis workflow, and I showed you all of these examples in an R script, but it would be better to include them as an RMD file, and once you get more experience working with R, you can start using GitHub and Git as a way to keep track of all of your changes in your analysis, so that you have a history of all the changes that you've made, and you can keep it on GitHub or and share with collaborators and have other people contribute to your analysis and your software. So that wraps up session 7 for today, and I'd like to thank you for watching and see you again next time.